Okay, this is Professor David J. De Las Rios. My problem for decision will be a problem on inscribed areas. This is under geometry. Okay, let's proceed. We are given a quarter circle over here. The radius of the quarter circle is 10 inches. And there is an inscribed rectangle over here. The given angle theta here is with the value of 22.35 degrees. Meaning from this point here up to this, with respect to the horizontal, theta is 22.35 degrees. This is a quarter circle, so this side here, with respect to this, is actually 90 degrees. Okay, 90 degrees. So if this dotted line bisects the so-called quarter circle at the middle, supposed to be this angle here is 45 degrees. This angle is 45 degrees. The problem is asking if angle theta is 22.35 degrees and the radius of the quarter circle is 10 inches, what will be the area of the inscribed rectangle? Inscribed, the one that could be cut from the quarter circle. Okay, let's proceed with the solution. For a rectangle, this should be the length and this should be the width. So I represented half of the width, this one, to be x. This is x also. So the total length of the inscribed rectangle will be 2x. That's the total length. And the total width, this one, is represented by y. So this is actually the width. So for us to get the area of the inscribed rectangle from the 1/4 quarter circle, okay, to get the area, we must know the value of x and y. This is unknown, this is unknown, this is unknown. So for us to get the value, we'll get 2x here multiplied by y, and that will be the total area. So in here, for a rectangle, the area is actually length times width. And the total length is actually x plus x. It should be 2x multiplied by y. Okay? So for the meantime, we call this equation number 1. Okay, let's try to bring out two resulting right triangles from the given figure. We'll try to bring out this one here, the bigger one. Okay, this one. Here is this. The dotted line is actually equivalent to the radius, and that radius is 10 inches. And this should be 90 degrees, right? So actually we are bringing out the bigger right triangle. It is this. So the opposite side is actually x. And the total adjacent side, considering the 22.35 degrees that was given, it should be this length here plus z. Z will be from this point here to this. So it will be a z plus y. And the second resulting triangle emanating from the quarter circle, it should be the smaller one. This one here. This should be a 90-degree angle. And since this is a quarter circle, this should be 90 degrees. So half of it will be 45 degrees. So from the horizontal line up to this is 45 degrees. So I place it here 45 degrees. This height here will be x, same as that one. And this is z. This is z. Okay, there are actually three variables involved. So we must have to eliminate this c here to compute for the value of x and y. Okay, let's try to bring out the bigger right triangle. We take the sine of 22.35. The sine of this angle will be the opposite over the hypotenuse. So it will be x over 10. X now will be 10 sine of 22.35 degrees. So x will be 10 times the sine of 22.35 degrees. So this should be 10 times 0.38. Sine of 22.35 is 0.38. So x now will be 3.8 inches. So we now know that this value here is 3.8 inches. This is also 3.8 inches. Okay, so actually we now know the total length of the inscribed rectangle. It is twice x. It is this, right? So our only problem now is y. Okay, let's try to take the cosine of 22.35 degrees. Take the cosine of this. Okay, so we will be having a relation of z and y in terms of x. Cosine of 22.35 degrees, cosine of this angle will be this side here over this. So it is actually z plus y over 10. C plus y now, cross multiply, it will be 10 times cosine of 22.35. C plus y will be 10 times cosine of 22.35. This is an almost unity value. 10 times 9.925 will be, meaning z plus y is 9.25. This equation here. We cannot just take the value y here and substitute on equation number 1 because there is an unknown z here. We must have to compute first the value of the unknown z for us to compute for y. Right? We now use this right triangle here, so we proceed with the other right triangle that involves the 45 degrees. This portion here, this small one, this is 45 degrees. This is x and this is z. So if we try to take the tangent of 45 degrees, to get the relation of x and z, take the tangent. Tangent of 45 will be opposite over adjacent. Tangent of 45 degrees is actually x over z. So x now will be z times tangent of 45 degrees. 45 degrees is a special angle. The tangent of 45 is actually 1. So x now will be equal to z times 1. Or x is equal to z. Because we now know x, right? So z is also 3.8 inches. This portion here is also 3.8 inches. Right? I will check my camera. So using equation number 1, where is equation number 1? Oh, no, not equation number 1. This should be equation number 2. This is 1, this should be equation 2. So for this one here, it should be using equation 2. So using this relation equation number 2, we now know the value of z, so we could compute for y. Z plus y is 9.25, and z is actually 3.8 inches. So y now will be 9.25 minus 3.8, and y will be 5.45 inches. Meaning the unknown width, this one, is 5.45 inches. So we now know x, we now know y. We'll go back to equation number 1. So the area of the inscribed rectangle now will be, we'll follow equation number 1, 2 times x, which is 3.8, times the value y, which is 5.45. The area of the inscribed rectangle now will be 41.42. We read this square inches. Square inches is actually n to the second power. We read that in engineering as square inches. or this should just be simply square inches. But we don't usually use this one in engineering. We read the square inches as simply n's quantity square, meaning an n's by n's is actually, it's loss of exponent, n's to the second power, or we read this as square inches. So the unknown area of the inscribed rectangle is actually 41.42 square inches. That's it. Okay. So as you can see, the problem is actually solved by using our knowledge of trigonometry. Good evening from Los Angeles.